So my name is David. I'm going to be talking about fully homomorphic encryption, which is my field of research. I'll try to be very fast without skipping important concepts that I want to share with you guys. So homomorphism is a characteristic that comes from mathematics way before encryption. And it means that there are certain functions that carries properties to the result of that function, in a sense that if you have a function f that you can apply between two operands, like f of a operator, whatever that is, b, should be equal to f operating in a and the operator on fb. So what is the meaning of this? Is that for encryption, if you have a encryption function that satisfies this property, that means that any operation that you do, at least the operations related to your scheme that you do on the encrypted domain, when you decrypt, will be equivalent to the same kind of operation on the plain text data. So a quick example of this is like over addition and multiplication. If you have two ciphertexts, two numbers, and then you encrypt those two numbers and you bring that to the ciphertext domain, if you add them together and you decrypt, you should have the equivalent result to add in the plain text. So that would be true for other operations as well. So here I bring like a very simplified but useful description of homomorphic encryption alone, which is the ability of computing on the encrypted domain, but also fully homomorphic encryption, which is the ability of operating any operation available on the plain text. You'll be able to operate on the ciphertext as well. But in a lower level, for the people that are building like circuits and are trying to do computers or programs on the encrypted data, that would be the ability of building gates that are able to operate on encrypted data. So the major FHE schemes right now, they are asymmetric, they are noisy, they have a lot of noise on that. They are lattice-based. Lattice is the ideal. Lattice is a mathematical tool that they use as a source of homomorphism, the other schemes. And they are mostly impractical in a sense that if in the plain text domain they can operate on a certain large data set, the same large data set when encrypted cannot be computed on the encrypted domain. So in that sense, they are impracticable, so they cannot be implemented under polynomial time. So this is a image that shows current FHE schemes. On the top, you see the scheme itself, and on the column, gray column, you see the libraries that are implementing those. I'm not going to talk about them. My research is building a new FHE scheme. So it's called XLogos. It operates over exterior product spaces, which is a mathematical construction developed by a bunch of people, but like Grassman, Hamilton, but that were put together by Clifford. So Clifford combined inner product spaces with exterior product spaces and created the Clifford algebra. And it is interesting because it is symmetric and asymmetric at the same time. And it builds a new kind of product called geometric product. And every time you multiply vectors, they grow in dimension. So you have a vector A times a vector B in, like, let's say 3 dimensions. When you multiply them together, you go to the 4th dimension, and so on and so forth. So it is very famous. This geometric algebra is very used in physics, very common in engineering, and in computer science, it is very used for games. Like a lot of people use that for implementing games, developing games, but XLogos is the first use of geometric algebra for encryption. So a bunch of differences compared to the other schemes. It is symmetric, does not use noise at all. It is based on geometric algebra, and it is space and time efficient. So There is something called ciphertext expansion in fully homomorphic encryption, which is how much your ciphertext grows when you encrypt something. This is a serious problem in all the other FHE schemes, and also the time for encrypting, decrypting, and doing the operations. In our library, this is really efficient to the point of us being able to implement a real-time video encryption using X logos. So a little bit of math here. The main object that we operate on is the multivector, which is just a collection of vector of different dimensions. So we have a scalar, a vector, a bivector, and a trivector. Addition of two multivectors is you just add the corresponding components, and of two different multivectors. The scalar multiplication, you just multiply the scalar by all the coefficients of the multivector, and then we arrive at the most significant product and also operation that we have in geometric algebra, which is the geometric product, which is a combination of a dot product, which is symmetric, and a wedge product, which is anti-symmetric, which creates a very nice property, starting for the fact that wedge product has no inverse. So once you multiply, there's no way to come back. And a basic example here of the implementation of the geometric product, if you have multivector A, multivector B, you're going to multiply them together to obtain C, and this is the implementation of the geometric product. And we ended up developing an edge product, which is the same construction of the geometric product, but we put an absolute value on the wedge part, so we can avoid negative numbers. This is just for killing the anti-symmetry, because sometimes we want to commute. So we created this edge product, which is identified by the diamond symbol. And then we have, like, pretty quick, some other functions from geometric algebra, just like involutions, which is changing the signs of the coefficients. Rationalize, which is a one-way function. You enter a multivector as input to get a scalar. There is no way to come back. The inverse of a multivector is this operation that combines involutions with the rationalize. And then we explore the concept of non-invertible multivectors, and that's probably the best reason that we give every time people ask why geometric algebra. Like among many other constructions, why not number theory? Why not bitwise operations? Why geometric algebra? Because geometric algebra is the only system in mathematics so far, to the best of our knowledge, that is able to extract meaning from non-invertible objects. So once you have, for instance, a matrix in linear algebra that is non-invertible, that matrix is called a singular matrix, right? The norm is 0, the determinant is, the inverse is undefined. So it's like multiplying something by 0. If I get number 5 or number 8 or number x and multiply by 0, this is a non-invertible operation, right? So everything that you multiply by 0 is gone. So, but geometric algebra gives you special tools that allows you, from a new type of result like that, something multiplied by 0, you can extract meaning. Maybe not the element that you multiplied, but probably the meaning that will lead you to find your answer. So this is what most of FHE schemes are looking for. If you encrypt A and you encrypt B, and you do addition or multiplication, and then you decrypt them, it should be equivalent to A plus B and A times B. But we are looking for this. This is a contribution of a French research group that they said that it's not enough to be able to do once. You need to allow general purpose computation on encrypted data. You should be able to do any sequence, any arbitrary sequence of any arbitrary operation. So this is way harder, but if you are able to do that, then you can build a program on encrypted data. It's not going. Okay, so our solution starts with reducing the dimensionality. We start as a 3D multivector, then we go to 2D just to explore some special properties of 2D because the implementation is dimension sensitive. So in 2D we have a strong isometry. So we use this isometry and we convert each coefficient of a 2D multivector to matrices, and then we can come back from matrices to multivector again. And we can use this formula if we don't like to work with matrices. We can keep everything contained on the geometric algebra. And this is one example of the encryption primitive. So you have secret keys, multivectors identified by S1 and S2. And then if you want to encrypt a multivector A, which represents a message, you just perform a triple geometric product, S1 and S2, with the message in the middle. You do that for A and B. And this is non-commutative, so basically you create a sandwich where the message is hidden between two encrypted, two secret multivectors. Then, with the support of a matrix that we call E, we create the isometry between two scalars A and B multiplied together. And if we put A and B in matrix format, and we put E in the middle, and we multiply those two matrices, is isometric to the multiplication of the scalars A and B. So that was developed so we could be multiplicative homomorphic, because being additive homomorphic is easier, and that was our solution for achieving multiplicative homomorphic. So the same thing happens in the encrypted domain. We create the matrix O, which we include the inverses of the keys in order to kill any undesired propagation of the keys during the multiplication process. So here we show two ciphertexts like CA multiplying CB, and through the elimination here, we will end up having only S1, the sandwich again, like the triple product, A and B multiplying together in the middle, and S2. So whenever we decrypt, we end up with the same multiplication that we showed in the plaintext domain. So this is a quick view of our implementation. We get a multivector in 3D. We create pairs of 2D multivectors. We do this for every element. So we have here two plaintext A and B. And then we do that for the secret key as well as creating S1 and S2. And then this is the setup for the encryption. So from the secret key S, we create pairs of 2D multivectors. We create non-invertible multivector G, which is secret. And the only reason we are creating this G is because we are going to perform a destructive operation that is going to basically lose the information. Then we don't use any matrix, so we convert that matrix E to a multivector. And then we create this multivector O, which is the encryption of the E divided by the magnitude of the secret non-invertible multivector G. And then we pick just a bit size for our random coefficients. Why? Because this is the way that we pack multivectors. We get a message A, which is just a number, like 5, 10, 15, and then we use random values to populate all the coefficients of the multivector, but in the end, we do a balance between the value that we are packing and subtracting all the other random values. Why? Because we want to recover the scalar this way. We want to unpack A by adding all the coefficients. So the sum of the coefficients should add to my plaintext. And this is the encryption process. So we pack using our random packing scheme a message. We convert that 3D message in 2D pairs of multivectors. Then we apply the destructive method that I mentioned. So when I get a non-invertible multivector and I multiply by anything, it's just like multiplying 0 by anything. You lose that information. So we do that using the edge product that we created. And then, this is wrong, I'm so sorry about that. It should be M prime here and M2 prime. So we encrypt the transformed messages, creating C1 and C2. And then we pack again to 3D multivectors. The decryption is just undoing that, and then a valid question is, if you lose the information, how can you recover? Well, we don't recover those multivectors anymore. So the multivectors are truly gone. What we recover is this MR here that we call the meaning of that information. So we recover a trace of the information that combined with the secret operators that we have, we can get the magnitude of that lost multivector, never the multivector again. But we are able to recover the message. So that's the most important thing. So we don't care about the multivector. The more convoluted it is, the more random it is, the best for encryption, as long as we get the scalar that we are encrypting. So we have addition, we have multiplication, that in the plaintext and then ciphertext domain. And some highlights here is that whenever an operation is available to us in the 3D setting, we use the 3D setting. Whenever, and you might ask, like, what is the difference? It's because some operations are dimension sensitive. Not everything is available in all dimensions. For instance, we could not find an inverse in 7 dimensions. And we were reading a book, and the author said that it's probably because there is no inverse in 7 dimensions. So some operations we end up not finding some of these resources. So what we are doing right now is jumping between dimensions. Every time we need something that is not available here, either we go 1 dimension down or 1 dimension up, we get that result and we come back. So our multivector O is a key component because this is what allows us to be multiplicative homomorphic on the encrypted domain. All the ciphertexts have no inverse, so that kills a lot of cryptanalysis. For instance, one of the most interesting attacks is generate a bunch of ciphertexts from known plaintext, pack them as square matrices, and calculating the determinant of the matrix. So if you can get a number that reveals after like millions of samples, reveals to be a common divisor, you might end up finding some information learning from that ciphertext. But if you have no invariable ciphertext, that attack is already compromised. So initial tests for indistinguishability are passing, and the scheme is very small. It's implemented, it's running on Amazon, and it's very simple. So one of the appeals of this scheme is that we can show to someone like pretty fast. It's a few lines of code, and you can learn everything. And on top of everything I showed here, we can use 3D encryption to enable and disable homomorphism, because some people think that homomorphism can be bad because people can learn from homomorphism. So we decided to do this. This is the last step. So we have our encrypted multivector, our encrypted ciphertext, and we decided to create an operation that kills the homomorphism. So we have the ciphertext that will work with homomorphic operations, but if we lock this and we created this multivector sharp in there, that operation annihilates homomorphism. So of course it's a second pair of keys. So if we give these keys only to the people that is allowed to operate homomorphically, not to see because it cannot do decryption. So that is a plus on this scheme. So security characteristics. So we work under the assumption that it's really hard to break under determinacy. So this scheme creates systems of equation that has always the double size of unknowns compared to the number of unique equations that you can come up with. So plaintext and ciphertext have no inverse. The norm is 0 or goes to infinity. And the encryption function has a destructive method inside, which really loses the information. You can only get the meaning. So we have a third-party cryptanalysis going on right now. I went to Toronto like recently, and I did a presentation. I didn't speak in there. I did a workshop, and that was the first time that we showed the encryption in public, and we got a lot of feedback. And DARPA was there, NIST was there, all the big techs, and NIST approached us and invited us to participate on the post-quantum cryptography group informally, because the deadline is ended in 2017, so officially we cannot be part of that. But they asked us to submit our encryption. We submitted. We passed the first round, and what happened is they are going to send us to the second round right now. They already gave us feedback on how to improve the scheme. This feedback is already implemented. They are being very helpful in that sense, because NIST decided to not have any more a standard for anything. They decided to have multiple recommended solutions for security. Dr. Jonathan Katz is a very known.
David, you're like 7 minutes overall.
Oh, I'm so sorry. All right, so, well, third-party cryptanalysis is going on. So we expect to have news about that pretty soon. Thank you.